Come on.
The very first on page 3, the very top, I've given you this before, but it just underscores that dyslipidemias are considered a major risk factor for the development of heart disease. Now, you can develop heart disease without elevated lipids. There's all kinds of things that go into having cardiac disease, arterial disease. Lipids is one of them. So it just lists down there not only heart disease, but peripheral vascular disease. So people who develop atherosclerosis in other beds, like their calves, they get intermittent claudication in their necks, other major arterial, those three, the brain. So strokes, gangrene, amputations, limited disabilities just because they can't walk very far. All of those are the lipids are contributed to that atherosclerotic process. So I gave you this before. 600,000 people in the U.S. died of heart disease in 2010, and that's about, I think it was 171 per 100,000 people. And in Oklahoma, men from heart disease, 235 per 100,000. So quite a problem in this state. Hadn't changed since I talked to you about 2 weeks ago. Stroke, still the third leading cause of death in the United States. Hypertension, #1 risk factor underlying that. Okay. So let's look at lipoproteins. So the body is amazing in how it handles lipids. It is such a complex. We just hit it superficially. In understanding and everything that it does. I think in your lifetime you will see many more drugs that are going to target some of these smaller proteins that regulate the movement of fats in between lipoproteins. So I think this will just become a bigger industry. There's lots of money in it. So that always drives things in. Follow the money, it always goes that way. So I think a lot more drugs in this category will come about. So let's look at that first table. The big 5 lipoproteins are chylomicrons, LDL, HDL, IDL, and okay. Now, when you look at how they're classified, it's based on their density. Okay. So density, it's looking at fat composition is usually going to determine a lot of their density. So the very low density lipoproteins usually have more fat in them compared to HDL, which is the least dense, least weight, or the most dense, heaviest weight, lowest amount of fat. So that's a very crude. This is just a generic lipoprotein. So what you see on the outside of this picture is you see this is the core full of mostly those things that are not very water soluble. So triglycerides would be in there, cholesterol esters. On the outside, you've got cholesterol. You have proteins, those apoproteins that have made several functions. We'll talk about those in a minute. That's what these are represented by. So this is a pretty typical. All of them will differ. They will have, and they mostly differ by how much protein they have and what type of protein they have. They also differ in how much is in that core. How much triglycerides, how much cholesterol is in that core. So if you look down through their functions, chylomicrons are very large. They're the biggest of all the lipoproteins. So chylomicrons at the top, HDL at the bottom. So chylomicrons, if you look across that top, diameter-wise, they're huge. Look at them compared to HDL. They are 75 to 1,200 nanometers versus 5 to 12. So chylomicrons are huge. The more fat you eat in a meal, the bigger those chylomicrons are. So fat isn't very soluble. So the body has to do something to package it in order to put it into the bloodstream so that it will travel. So the role, why all these different lipoproteins? What is the role of them? They're transferring what? Fatty materials. So what are fatty materials? What would be the names of them?
Triglycerides.
Triglycerides. So they're carrying glycerol and free fatty acids in the form of triglycerides, sometimes separate, and they transfer it out to the body, either to store it. Mostly the periphery, the muscle and the adipose tissue are going to take it up and they're going to store it away. But the body can use free fatty acids as an energy source. The heart does, all the muscles do. When you're exercising, you rely a lot on free fatty acids because you can run through your glycogen stores pretty quickly. So this is a way to get things out to the different transporting, out to the different cells of the body, tissues of the body. The other thing is that we make our cell membranes out of some of these. So building structure, they provide that. Energy source, they provide that. Immediate and long term. You'll notice also on the side I've listed those apoproteins that they are associated with. We'll talk about those in a little bit and what their function is. So chylomicrons created after you eat. So all the fat that you synthesize or that you take in, the body will make into these chylomicrons, and then they can eventually enter into the bloodstream. VLDLs, IDLs, and LDLs are kind of a continuum. VLDLs are made by the liver. The liver puts them out, and then the body has ways to break them down and release those free fatty acids into an intermediate densely lipoprotein, and then the LDL, which you know. So LDL is another one of the major cholesterol components in the body. So if you look down through here, the percent of protein increases as you get down to HDL. Chylomicrons have very little protein. It's not their job. HDL, on the other hand, has the highest percent, 50%. Has a lot of proteins on the surface. And they have it on that cell surface because they are the major lipoprotein that transfers things back and forth between all the other lipoproteins. If you look at triglyceride composition, you see that chylomicrons, they're the biggest, 88%. They're almost all fat. That's why they're so light. And then you've got the HDL very low. Then look at your cholesterol esters. You see that LDL, biggest one. You already know that. It's the one that carries the cholesterol in the body. And then the other ones to a lesser extent. This kind of shows you their size in a different range. You're looking at density on the y-axis, and on the x-axis you're looking at diameter. So you see those chylomicrons are huge. One of the reasons you wait about 12 hours before you do a fasting lipid profile in patients after they eat is because if you don't, you tend to pick up those chylomicrons. So we don't want to know about those in terms of treating somebody's lipids or figuring out what their baseline lipid is. So that's one of the reasons we wait, is for that to be cleared out of the bloodstream. Because it's very meal dependent. We don't want to know what happened with one meal. We want to know basically from day to day, what do you do? What does your lipid composition look like? Then you see VLDLs and then this Chylomicron remnant, which is once we start stripping triglycerides out of that, we get a remnant. Then got that intermediate IDL, then LDL, and then the HDL. Another way to look at them is this one, color-coded. But what I like that they've done is they show you these are pro-atherogenic lipoproteins. If there's too many of them and they linger too long and they get where they shouldn't be, they set up the atherosclerosis. They start forming those foam cells and the fatty streaks. Whereas HDLs, you're anti-atherogenic. because they pick up cholesterol in the periphery and bring it back to the liver. I think we've hit most of these. This kind of gives a cartoon picture, maybe a little bit easier to look at. Again, that core of triglycerides and cholesterol esters. Outside is cholesterol and those proteins. There shows you a chylomicron in a little bit different form. Here's the outside, this is the inside. And here are these big proteins. Those proteins serve different functions. If you look in the middle, it shows you. They give structure to the lipoprotein. They also serve as ligands. What are ligands? Talked about at the very beginning. The receptor. They're proteins that will interact with the receptor. Let's see what on this one. But they are the ones that allow them to attach to either an enzyme that they need that will metabolize them, an enzyme that will transfer something from them to someone else, or will allow them to connect with the liver or re-enter the liver. Okay. Let's see, we hit them all. Structure, ligand, lipoprotein formation. Lipoproteins are identified to some degree, not only by their size and density, but also by which of these proteins is sitting there. Deficiencies of some of those proteins can then set the person up to have a more atherogenic profile. So we're just now getting to appreciate like ApoE. It has many different types. There's at least 4 that I know of. One of them is associated, ApoE4 is associated with increase in Alzheimer's disease. ApoE2 is much more associated with atherogenesis. So as we get better understanding of deficiencies or overactivity of these enzymes, we'll direct drugs that way. So looking down at the chart at the bottom of page 3, there are 4 of these that, 3 I highlighted and 1 I added as I went through. So you'll see the A types. A1 is most important. Star it if you can't, it should be, I see it highlighted. That one's really important for HDL. It's where HDLs start. So you've got to have A1, which then the body builds around to make your HDLs. If you look down at B1, B1 is a very important protein. You see it is on VLDLs, IDLs, LDLs, and Lp(a). The importance of it is that it's the ligand for the LDL receptor. You have LDL receptors all over your body. Liver is really important, but all the cells have them so that they can take it up and use it for the cholesterol or the free fatty acids. Chylomicrons have this V48. Only the chylomicrons carry that until they start to be stripped down for their parts. The C chylomicrons of those C2 is very important. They're all important, but the ones that we're going to talk about. It's a cofactor for lipoprotein lipase. Very important enzyme in your bloodstream. As your body, as those chylomicrons go past, so as chylomicrons are moving through the bloodstream, there are these little enzymes that are sticking up, just waiting for them to pass by, and that's lipoprotein lipase. It hooks them and starts to strip the triglycerides off of them. And that's what creates that chylomicron remnant. Really important, because when we get to diabetes, that enzyme is very insulin sensitive. So somebody comes in and they're way out of control, their diabetes is poorly controlled, they're not making a lot of insulin. Guess where their triglycerides are? Very high. So when I start telling you, always correct the underlying problem before you treat the triglycerides, that's one of the reasons. We replace the insulin, their triglycerides will go down. They may not go to normal, but they will go down quite a bit. The very last one, ApoA, is a structural protein for Lp(a). Lp(a) is we are beginning to recognize that it is a much more atherogenic lipoprotein. It inhibits plasminogen activation on Lp(a). So what's plasminogen's role? Plasminogen gets converted to plasmin, fibrinogen to fibrin degradation products. Very good. Okay, if you look at the next page, it gives you a summary of each of those lipoproteins. So chylomicrons, we talked about them already. These are formed by what you eat. It's the exogenous pathway. The body always has usually multiple pathways to get done what it needs to get done. So when you eat dietary fat, the body has a way to process it. Okay? So it starts with those chylomicrons. Again, the size and the amount will depend on how much fat you ate in what length of time. Again, it takes about 12 hours to clear those, 9 to 12 hours. Chylomicron remnants. Just kind of cartoon drawing of them. Again, chylomicron remnants are a product of that lipoprotein lipase activity on a chylomicron. Strips out fatty acids, ApoA, and C2 and C3. HDL is usually very close by and is picking these things up. So it not only takes up cholesterol from the periphery, it also is in the bloodstream to take these up. Chylomicron remnants usually are going to head back to the liver, and the liver will reprocess them. Okay? If they stay around too long, they don't get cleared, then they are pro-atherogenic. So they will promote atherogenesis. They'll move into the cell wall, not cell wall, the intima of the arteries, and they can start a fatty streak there. That's just another picture of them. Oh, that's why I put it in there. This is to show you the HDL hanging around to pick up these things that are released. So just another way to look at what we just talked about. VLDLs are made by the liver. They are very triglyceride rich. So when we're determining the level of triglycerides, we can well, I won't go there yet. I'll get there later. LDLs are metabolized to, again, triglycerides are stripped out of that VLDL, and they become that intermediate density lipoproteins. They can return to the liver, be reprocessed. They also continue to be stripped down of their triglycerides, and guess what they become? LDL. So if we can knock down the production of VLDL, what will happen to LDL? It'll go down. And we'll see that when we're using some of these drugs. So IDL, again, is pro-atherogenic if not removed. LDL is pro-atherogenic if there's too much of it. So let's go through the Ldl points. So these are derived from VLDL and IDL. You could consider LDL a remnant of IDL. They carry the majority of cholesterol that's in the circulation. That's important to know. They are different sizes. these. Their density will determine, the more dense they are, the more problematic they can become. So LDL just isn't LDL. So we have people who have buoyant LDL, they've got more triglyceride in them, they're probably not as atherogenic as those that are tighter or more dense. So look at the fourth bullet down there. Let's go through this. It's important. It'll probably be even more important to you guys as you move forward, because we'll be able to do panels and tell you what all your LDLs are and to know if they're as atherogenic as we think they are. So small, dense LDL particles are more atherogenic because they're harder to clear out of the circulation. They don't fit on that LDL receptor as well, so they stay in the circulation longer. The longer they are available, the more likely they are to move into the intima of the arteries. Okay. So they're smaller, they can get into that space easier. They're also more susceptible to oxidation. That's a problem, because they produce those free radicals, which are more dangerous. They are more likely to be taken out by macrophages. If the macrophage doesn't get rid of them, then they eventually become those foam cells, which then lead to the development of that fatty streak. Okay. See why they're important? So the small LDLs are more problematic to us than the more buoyant, bigger LDLs. HDLs. I put this in here just to show you all the things that HDLs do. They're more than just cholesterol transport. They have the ability to decrease inflammation. They decrease oxidation. They improve the endothelial function and integrity, involved in homeostasis. They're helpful in diabetes. The higher the HDL in diabetic, the better off they are. So multiple functions. There's also a wide range of HDLs. There's at least 5 of them, 2 of them that we know enough about now to have some idea. They are different shapes. Lipid poor ApoA1 is an HDL that's given up all of its cholesterol and it's ready to receive more. So it may have already been by the liver, it's dumped all its cholesterol, it's heading back out to get more. So they can be a discoid shape, they can be a spherical shape, lots of different densities. You see now we even appreciate that for HDL3, there's even subtypes of it. Depends on how much cholesterol they're carrying and if they've headed back to the liver or not. So just kind of a reminder here, reminder slide. VLDL in chylomicrons converted into high triglyceride content, stripped away so that cells can take it up and get the fatty acids out. IDL, a remnant, LDL, remnants. They head back to the liver. The liver, the biggest thing we want to do with those is get them back to the liver and get the liver to take them back up. One of the big problems that occurs in the Caucasian population is about 1 in 500 have problems with that LDL receptor. So those are people usually that have very high LDLs. They can't clear it. They can make it all day. Everything else seems to work, but they do not have the receptor population, so they cannot clear LDL as fast. HDL, just a reminder about it, it picks up the cholesterol. It has the ability to cause cholesterol to efflux out of the cell walls of the arteries, picks it back up, takes it to the liver, dumps it out, comes back. So HDL doesn't get reprocessed like these others do. These actually enter into the liver and are taken apart, disassembled, and then reassembled into something else down the road. HDL doesn't get that way. It stays active in terms of its ability to pick up cholesterol and move back and forth from the liver out to the periphery and then back again. This is just a summary slide. I think I've said everything here. Yep. Sometimes I like two slides. They show things a little bit different ways, so I keep them in there. So here's HDL. Here's ApoA1. HDLs can have multiple of those. That's a good thing. So if you look at on page 5 is where I am. Major structural protein of HDL. There are all kinds of receptors that HDL interacts with, and this is one of its major proteins that can interact with those receptors. You'll see scavenger receptors listed down there. You have them on the liver, you have them out in the peripheral cells as well, which helps take up and get cholesterol out of circulation. B48 we talked about, those are on chylomicrons only. Not really sure what their function is. They cannot interact with receptors, but and there's usually only one on a chylomicron. It's one thing that kind of notes them. The B100 is important because that's what interacts with the Ldl receptor on the liver. So VLDL, LDL, IDL all have that apoprotein to be able to work. So it's a ligand. C2 is important because it is a cofactor for lipoprotein lipase enzyme. That is a really important enzyme. And for it to work well and for you to be able to metabolize triglycerides appropriately, you've got to have that functioning. And then ApoA is synthesized by the liver. It's linked to atherosclerosis. The higher your Lp(a), especially when it's attached to a LDL, makes that a very atherogenic lipoprotein. Questions about those? Okay. Enzymes that are important. There's two that I picked. There's two slides here. Okay. So this one shows chylomicron coming through. Here's the lipoprotein lipase. You see the ApoC2 up there. And as that chylomicron comes through, it will help release those free fatty acids, and I use this one to remind you that it's an energy source. For its action, I like this one better. So here's those lipoprotein lipase in the arteries. Again, as that chylomicron, or probably veins too, as it comes through, it's going to snag that chylomicron and it's going to break them down. Okay, really important. You also have one called hepatolipase. It is on the liver only. And it deals with a lot more of the different lipoproteins, but also helps to break them down into their component parts. Okay, any questions about those? Okay, let's go through the exogenous and endogenous and reverse transfer. So this is the endogenous system. So this, you know it is because you're at the liver cell. I'm sorry, intestinal cell. So free fatty acids are coming in from your diet. You are the enterocyte is really important because it puts these things together, creates the chylomicron. And lo and behold, it goes into the lymph system. And from there, it heads to the liver. I like this slide because it breaks it down into all the parts. So there's the intestinal cell, there's the lymph, gets to the liver, and the liver then eventually HDL comes into contact with it and it donates those apoproteins. Those are important because that's what causes it to become what they call a mature chylomicron. At that point, because of that C2, it can hook onto that lipoprotein lipase and be converted into a chylomicron remnant. Okay. And then the remnant, if everything goes well, heads back to the liver. That's the exogenous pathway. Exogenous meaning it's outside the body. You're bringing it in. Here's the endogenous pathway. This one starts for the liver. The liver makes a lot of things, and it makes most of your lipoproteins. So it starts with triglyceride and a cholesterol, and with those apoproteins, it assembles a VLDL. Okay. So VLDLs are the endogenous pathway. They're the beginning. Chylomicrons are the product of the exogenous. Nascent, what's nascent mean?
New.
Born, created. So it means it's been created by the body, not something you have eaten or taken in. Again, here's HDL, faithful and loyal. C2 and ApoE added, and again, that allows it to be metabolized by that lipoprotein lipase as it goes through the bloodstream. And the product of that catabolism is IDL. IDL continues to be catabolized until we get to VLDL. So that lipoprotein lipase is just stripping triglyceride away until we get pretty much a cholesterol core. And so back on that one chart that I showed you, the heaviest concentration is in the lipoprotein, is in the LDL, sorry. This is just another way of looking at it. So that once it enters the lymph, the chylomicron, it will eventually reemerge, and this shows you that same, just in a different picture, with it being stripped down, some of it, the fatty acids going into the periphery. I like this one because it shows you they can get into the intima of the blood vessels and start to cause a fatty streak, an atheroma. What we want it to do is keep going back up to the liver. Okay. This one is showing you the endogenous. Same thing, it's just a different picture. Has all the apoproteins, a little bit better color. Questions about those? So a lot of what we do with drugs is we try to interrupt this process. Okay? We decrease the amount of cholesterol the liver makes. Lo and behold, the liver is very sensitive to how much cholesterol is in its cells. If it goes down, it will rev back up. It's like, okay, it'll pull more in from the bloodstream. It'll increase those receptors and it'll pull more LDL and VLDL. It'll pull all of these back in. The other is it just won't make as much VLDL. It won't put it out until it can get its production up. So by interacting with all those different steps as much as we can decrease somebody's cholesterol. Okay. Let's see, I thought I had a reverse transport. Let's talk about reverse transport. I've alluded to it. Reverse transport is that picking up of HDL, picking up cholesterol in the periphery and bringing it back to the liver. I know I've got that picture. Let's see what we do with it. I know, I skipped some stuff. This kind of puts into picture what I just said word-wise. So anytime that the liver is perceiving that it has not enough cholesterol, then it upregulates the amount of LDL receptors. And it'll pull that LDL in, it will disassemble it, cholesterol levels will go up, and Once it hits a point where it's got enough internal cholesterol, then it'll down-regulate its receptors again. So if there's not enough cholesterol or substrate to then create cholesterol, it will start pulling it in from the periphery. So these two men, anybody know who they are? Goldstein and Brown. These are the people who, they're out of Dallas. Tim, where are you? Oh, not here. Dallas. So these are guys, Southwest Medical School. They discovered the Ldl receptor. It was huge because that made a lot of difference in our ability to treat and our understanding of how LDL was handled in the body. These guys won the Nobel Prize in 1985. It hadn't been that long since that was done. They won the Nobel Prize in Science that year for that discovery. See, and they don't even look that weird. Yeah. They look like they could be this day. I mean, right? Yeah. I mean, they don't look like they were 100 years ago. So it hadn't been that long ago. Weird. Okay, so let's go back over this again. So, dietary fat comes in, and we make chylomicrons. We call that what pathway? Exogenous pathway. So chylomicrons then are broken down by what enzyme? Lipoprotein Lipase, and create what? Chylomicron remnants. And where do they go, hopefully? Back here, remnant receptor. Different receptor. Okay. And the free fatty acids we strip out of the chylomicrons, where do they go? They go to the fat, and they go to the muscle. They actually have different lipoproteins on them that will direct them one way or the other, okay, that they can interact with the receptors. Okay, so then the liver puts out the LDL. We call that pathway what? The endogenous pathway. What breaks it down? Lipoprotein lipase, again, triglycerides, free fatty acids out to the periphery, and its intermediate is called IDL. What breaks it down? Lipoprotein lipase into LDL. LDL can come back to the liver, or it goes out to the periphery for uptake by the different cells. Okay, so that's the LDL cycle. Okay, got it? Got it. It's not that hard. Here's reverse transport. This doesn't show all of it, but some things it does is you've got LDL, you've got HDL circulating all over the place. And you have these deposits of cholesterol, and these are transport proteins, don't worry about them so much. These will efflux out of that, and HDL is going to pick it up, and it's going to bring it back to the liver. That SRB1 is those scavenger receptors. It is a target of some drug development right now. It's probably all of that. Okay, so let's look at the bottom of page 6. So, a man by the name of Fredrickson classified lipid disorders into patterns. Now, not everybody uses these, but it's still a nomenclature that I think is somewhat helpful. It divides the classification into 1 through 5. There's 1, there's 2A, 2B, 3, 4, and 5. The 2A and 2B you will see most commonly. It is extremely rare to see a 1. You just don't see chylomicron or class 1 very often. 2As, in 2A the primary problem is LDL. So if you look at their lipid panel, their LDL will be elevated, their total cholesterol will be elevated because of that. Their HDL can be normal, below, high. Triglycerides are usually normal. Have you had lab medicine over lipids?
Yes.
Yeah. Okay. So, what do you remember? You got, what's the equation? The total cholesterol equals what? It does what? Say it again. LDL plus HDL plus what? VLDL and divide by 5. Some people put in triglycerides, but what did you learn about LDL? Did we measure it directly?
No.
No, it is a calculated. You can request a lab to do that, but most of the time this is a calculated value. The lab will do it. I worked in a lipid clinic for a number of years, so thousands. When I left, we had like 3,500 patients. So I got to where I always eyeballed it. Occasionally I would find a miscalculation, but most of the time that you'll be right on. This equation breaks down when this number gets above 400. So sometimes you will get a lipid profile back that you don't have an LDL calculated. It's because the equation is not predictable very well after that. So with higher hypertriglyceridemia, usually you won't get an LDL calculated. So your total cholesterol is looking at kind of these big, now that you know there's multiple LDLs. So when you measure LDL or you calculate LDL in the bloodstream, you're just calculating a community. It's like saying we have 36 people in this, but it doesn't tell you the breakdown of men, women, ethnic groups, anything. Same with HDL. We're just measuring the whole population of HDL, the whole population of the LDL. Okay, so did you learn normal numbers? What is like a normal triglyceride? Less than 150. Triglycerides usually TG, less than 150 milligrams per deciliter. What about HDL? What's a normal for HDL? What does it depend on?
Sex.
Sex, gender. Okay, so you got men and women. Okay, so what'd you learn from men? Well, there isn't just one number. What'd you learn? What number did you learn?
Greater than 60 is the best.
40.
For age, yeah.
Under 40 is
Okay.
40.
Okay, so what is it criteria-wise? Metabolic syndrome, you talk about it?
less than 40 is bad.
Okay, for men, we would like to have them greater than 40. For women, we would like to have them greater than 50. Okay. Now, they can be any range. Less than, so there's a gender difference. If you see young women with low HDLs, that's bad, because usually our estrogen will keep it up. Usually, I would imagine most women in here are in the 60s to 70s. Michelle, well, if men in here exercise, they tend to have higher. Men tend to have a higher response to exercise and HDL than women do, because we always tend to stay high. So the higher the better here is one thing to keep in mind. But the criteria you ought to have, because of the diagnostic classifications, and I think it's 40 or 50 greater than. So men, I almost always expect them to be low, but young women I really worry about. When I've got young women your age in the 40s, that I'm concerned about. That's usually genetic, often time. Usually the higher the triglycerides, the lower the HDL. So when they calculate it, they're going to take total cholesterol, they're going to subtract LDL and the triglycerides to calculate the LDL. So did you learn a value for total cholesterol? usually that's a goal, okay? So less than 200. Now, if you've got really high HDL, you can have a very high or a higher than normal total cholesterol. So I never stop at total cholesterol. You're great, you're lower than 200, well, big deal, because you could have high triglycerides, low of these, and still have a normal total cholesterol. So total cholesterols, they are like a screening number. You really do need to look at the breakdown of what they are in order to know, because any combination here can lead to the same number. Somebody can have the same number and have derangements in one of those lipoproteins. Okay. So 2As, so if I said 2A pattern, someone says that to me, I know they've got an elevated LDL, HDL and triglycerides are probably normal. 2B is probably one of the more common ones you will see. A lot of diabetics have this. It is, their LDL is elevated, and usually their triglycerides are also mildly elevated. HDL usually is on the low side, because the higher those triglycerides get, the lower that HDL will go. Let me skip down to 4. 4 is primarily VLDLs. This 4 and 5 are usually genetically linked. Their parents usually had elevated triglycerides if they knew about it. Type 4s usually are in the 2,000 to 5,000 range. Now what did we say was normal? Less than 150. So 4s usually are above that up into the 1,000 range. The type 5s very high, 5 to 10,000. Those folks, 4s and 5s are at risk for pancreatitis, because hypertriglyceridemia is one of the things that can cause pancreatitis. Usually they have very low HDLs, and their LDLs you never see. You would have to have someone do a direct measurement in order to get that. Okay, questions about those? All right. Okay, so we talked LDL receptor, we've talked about. Let's go down to basic pathophysiology. So we've been through this before. Okay, so LDL or one of the others, the chylomicrons, the IDLs moving into the underneath the endothelial space. Again, macrophages capture them, they're oxidized, they form those foam cells, and eventually over time, over years, we get that plaque formation. So the earlier we can intervene, the better. Not so much with drugs, but with lifestyle. So getting kids to eat right, be healthy, maintain a good weight. But also knowing family history. So if you take care of kids, you've got to know what the family history is. If their parents had high LDLs, they are very likely to have high LDLs. The people we're worried about the most are the familial. Let me go to them real quick. Here's a picture of a 10-year-old. Okay, so she has got xanthomas everywhere because she has inherited the inability to pick of LDL receptors, so they tend to deposit in her periphery. She had her first heart attack at 8.
Oh.
So these are familial hypercholesterolemia. They can be heterozygous or homozygous. If they're homozygous, their LDLs are usually 300-400 and above. Okay. Normal, we're looking at about 100, 130. I saw several of these in the VA. I had one young man he had his first heart attack at 21, his mother at 16, and she died at 36. And she was the oldest in her family. The brothers all died earlier. So strong family history. I mean, these folks are easily identified because they developed the disease very early, and so intervention with them is very important. Even so with children, you would need to know this because you have to intervene in order to, these are very noticeable, but also to decrease the risk of atherosclerotic disease. Okay. Let's go back up. All right. This is a really good slide in terms of what it shows. So on the y-axis you have coronary artery disease relative risk. On the x-axis you have cholesterol, you have LDL, which actually goes from highest into low. So from 220 down to 100. And then on the z-line axis you have HDL from from its highest to its lowest. Okay? This is Framingham data. So if you look, these are folks that are in the best shape, or that have the best lipid profile. So their LDL's around 100, HDL around 85. But you see their risk is not 0, right? And as you increase, even if you hold that HDL at steady at 85, you see that as their LDL goes up, their risk for heart attack also goes up. Not very much, but there is an incremental risk. You see also, even with a normal LDL, as your HDL goes down, your risk goes up. People at the highest risk, back there, that highest red is the highest cholesterol quartile and the lowest HDL. So both are important. Our drugs go against LDL. HDL, we tend to look more at lifestyle. There aren't as many trials that have looked at raising HDL with drug and effect on cardiovascular outcome. I showed you this one before. This was out of the Mr. Fit trial. This is probably back in the 80s, 70s or 80s. So coronary risk ratio, plasma cholesterol. You see that once you hit a certain point, it's almost exponential. The slope of the line gets even steeper, so the risk keeps going up. So that's why the most of the drug therapy is targeting LDL. Even though it says plasma cholesterol, it's the LDL that's making up the majority of it. Questions? Okay, let's take a break. We'll come back about 7 or 8 after.